Hey everyone, this is Matt with Learn Everything About Design, and in today's video we're going to be creating some 3D printable spur gears in Plasticity. Now this is a request I got quite a long time ago to do because we did some videos about making different 3D printable gears inside of Fusion. Now unfortunately Fusion has a built-in script that was created by the guy that created the API for Fusion in general, and that's built in and it makes it a super easy task to do. That's not something that we have built currently in Plasticity that I'm aware of. It's certainly not in a default install, but there are loads of these different tools online that allow you to put in some various parameters and you can spit out things like a DXF or an SVG file, bring that into Plasticity and just extrude it as a solid. What we're going to be talking about today is going to be a pared down version of this. And what I mean by a pared down version of this, we're going to be creating some basic numbers in a spreadsheet that we can use to drive and dictate the geometry that we're creating. And so first thing that we need to do is we need to build a spreadsheet and look at some numbers. Now I'm using only Office, so this works in Excel, this works in Google Sheets, works in whatever different spreadsheet that you want to do. We're just going to do some very basic calculations. But there are three main numbers that we're going to use to drive it. I'm actually not going to be driving this first one, but I want to put it in so we understand it. So the first one is going to be our pressure angle. Now the pressure angle I'm going to set at 20 degrees by default. I'll just put degrees over here so we know it's an angle measurement. I'll talk about that once we start sketching and creating our curves so you understand what that means. The next one is going to be the module. Now I'm going to set this at 1 by default. This is going to be a variable that controls essentially the height of each tooth. Now, the number is not directly related to, let's say, 1 millimeter. We'll talk about that change once we build out the rest of the spreadsheet. And the last thing that I'm going to use to drive this is going to be the number of teeth. And for our example, I'm going to use 50, and that's just a quantity, right? It's not 50 millimeters, it's not 50 degrees, it's just a number. And then we're going to have some calculated values. So I'm going to just put calculated values down here. The first one that we're going to calculate is called the pitch diameter. Now the pitch diameter is going to be basically where the two gears are going to touch, the diameter at their contact point. Again, we're looking at straight spur gears. We're not looking at helical gears or herringbone style gears or anything like that. This is the basis for what we're doing. So with the pitch diameter, this is essentially equal to, and so in any of these spreadsheet tools, you're going to start with equals. It's going to be equal to the number of teeth times the module. And so for our case, this ends up being 50 millimeters. This is going to actually be our diameter value. So you can see that if you increase the module to 2, for example, we get 100 millimeters. If we reduce the number of teeth, it comes back down to 50. So I'm going to leave these at 50 and 1. It makes the visualization a bit easier as we're learning what these numbers do. The next number that we have is going to be our circular, and these may not be the exact names that you'll find if you search on like engineering forums or things like that, but this is essentially the distance that is between the two teeth. And again, once we start sketching this, I'll talk about these and I'll come back to these numbers. And so this is going to be equal to, we're going to put it in brackets, pi, I'm going to go out to 4 decimal places, times our pitch diameter, so this number here, and then that whole thing is going to be divided by the number of teeth that we have, and we'll hit enter. And so you can see in this case, because our pitch diameter and the number of teeth are the same, because our module is 1, that ends up just being pi. If the module was 2, that doubles it, and you can see that as we play around with these numbers, that we can affect change between these, again, just based on the way that these are created, because it takes the pitch diameter and it divides it by the number of teeth. So as the module and number of teeth change, these numbers will change as well. The next one that I want to do is going to be, I'm going to call this the tooth width at pitch. And so this is going to be the thickness of the tooth at the contact point. And so this is going to be equal to our circular pitch distance divided by 2. And so essentially what we're looking at, and I'm going to hop over here just to show you for a second. Essentially what we're looking at is let me bring back one of these curves. I think this is going to be our pitch diameter. They're going to be underneath it. Yeah, I moved everything. It's not going to work out very well. But let me go ahead and move this. I'm going to go ahead and move this one over. Let's move it 25 millimeters. I'll hide the rest of the stuff. So that way we can see what's going on. And we'll hide this one as well. All right, so as we're looking at this, our pitch diameter is essentially the point at which the two gears are going to come into contact. And so the numbers that we're calculating right now are essentially going to be the thickness of this tooth at this point. Now, this is 1.57 millimeters, and also the distance between the two opposing teeth, right? So if we look at the distance between the two sets of teeth as this thing is rotating around. And you'll notice that this is double the value. In this case, 3.14 because our pitch distance ends up being pi. And so those are the two distances we're calculating right now. The distance between two opposing teeth as this thing rotates and the thickness of one tooth at that pitch diameter. Now remember that pitch diameter, this is where two of the gears are going to be touching as this thing rotates around. So let's bring our spreadsheet back. I know this is a lot. If you don't have any interest in this, skip ahead in the video and you can just kind of copy what we did here. But just keep in mind, as we're trying to build these out, we're following roughly what a true spur gear would be, but I'm simplifying it because we're taking out a lot of different math that's needed to calculate this stuff. And when we're 3D printing plastic gears, most of those sort of engineering values that we need are going to be sort of moot anyways. It's not going to matter for what we're doing. All right, so first off, we've got our pitch diameter. Then we've got our pitch distance. So again, this is between two teeth. So from this tooth to this tooth at that pitch diameter. Then we've got our tooth width at the pitch. And so it's basically from the contact points through the thickness of that tooth. The next thing that we have is a measurement called the addendum. Now, the addendum, and there's also a dedendum. The addendum is basically the distance from this pitch diameter out to the end of our tooth, and the dedendum is the distance from this pitch diameter down to the root or that inside diameter. Now, again, these numbers in practice in engineering, there is a whole lot of other factors that go into this that we are skipping to simplify these numbers. But depending on how the gear is made, depending on tons of other factors, things like the pressure angle, these numbers are going to change. We're going to give a very simplified version of that. So at the basis of this, the addendum is going to be 1. I need equals 1 times our module. And again, that's going to be in millimeters. We're basically going to take that, we're going to add it to the pitch diameter, or add it to the radius, essentially. And the dedendum is going to be, I got to remember to hit equals, 1.25 times the module. And so again, this cell value right here. And in this case, it's 1.25. But again, if we change the module, if we change this to 2, those numbers go up, they double. We're going to keep it at 1 for our example. It simplifies things. Now, if we want to, we're going to calculate the tooth OD. So basically what we're going to do is it's going to be equal to 2 times the addendum value, and then we're going to add the pitch diameter. So add to that 50. And so this gives us an outside diameter of 52 millimeters. And again, I'll put millimeters here. Now the tooth ID, and again, these are names that I'm coming up with. These are not going to be the engineering names that you're going to find, but they are roughly the same. We are just not accounting for all the various factors that go into creating these. And so this one is going to be equal to the pitch diameter, so that 50, minus, in brackets, 2 times the dedendum, the amount that we're taking away. Because remember, the dedendum and the addendum, those are basically radius values. They're distances from the pitch diameter out to the end of the tooth or to the root of the tooth. And so to get the diameter value for a circle that we would want to draw, we're basically we're using these values. And so we have a circle of 47.5, we have a circle of 50, and we have a circle of 52. The 50 is that contact point between teeth. The 47 is going to be the root that we're creating. The 52 is going to be the outside that we're creating. The 1.57 is the thickness at basically that contact point. The 3.14 is the distance between the contact point on this tooth to the contact point on the next tooth. These are all important because, and essentially they're double, because as the gears rotate around, they need to be able to basically have this distance associated with it. So if we were to unwrap this and make like a rack and pinion, for example, we can still use these numbers to create the tooth pattern of the gears. And in this case, we're doing it in a circular fashion. But once again, I have simplified these numbers, taken out a lot of the math that goes into calculating some of these values. And the pressure angle, we are not driving any of these values with the pressure angle. We are going to be using just 20 degrees as our default pressure angle. 20, 22.5, 14.5. There's some standard numbers that you could use. For 3D printing, honestly, it's going to be more important that you work on the slicer settings than this pressure angle. We want a pressure angle, but the pressure angle is not going to have as much of an impact on what we're doing here for 3D prints. All right, so now that we have all those numbers, let's get started with a new design. So a new file, I'm going to clear the scene. I'm going to delete the default cube. I leave the default cube just because anybody that's getting started, they will have the default cube. If you're using Plasticity and you don't use the cube at all, I suggest saving a new startup scene after you delete it. That will just make sure that you don't have that at all. Also note that the units I'm using is millimeters. Grid size is 250. I do that because that's essentially a 3D printer base plate size for most of the printers on the market right now. And then lines every 25. That changes as soon as we go into a sketch or into creating our curves, but those are my base settings, so we have an idea of scale. All right, so I'm going to do everything from the top. You can do this by clicking on the top of Z, or you can use the numpad number 7. That'll get you there as well. You can also go down to the default planes and you can do the XY plane and click on that. That will get you to the same location. We're going to do everything from this top view. We're going to draw one gear and we're going to be using some of these, basically all the default tools. I'm going to try to avoid shortcuts whenever possible, but the shortcuts are really the way to go in Plasticity. I would strongly suggest getting comfortable with the handful of default ones, but we'll use all the button locations for this. So circle, if yours doesn't show the center circle, there's a little white arrow in the bottom right corner. If you hold down the left mouse button, it'll bring up the other options. So if you happen to be on ellipse or an arc or a 3-point circle, just make sure you hold down the left mouse button and then select the center circle. The shortcut key for that is Shift and C if you do want to remember it. Shift and A for a line, Shift and C for a circle. Those two come in pretty handy if you use them all the time. So we're going to snap to the origin. You notice it says origin X, X, Y, and Y. So this means that we're clicking on the origin, we're snapping at the X-axis and the Y-axis, and we're on the XY plane. So it's exactly where we want to be. That's what happens by default. There is also an option for snapping to in 2D. That's persistent. So what we're going to just make sure that over here on the right-hand side, make sure that you are set to object snapping. You can also snap to grid if you want to. I don't personally turn that on, but if you do want that, then go ahead and do it. But we're going to snap there. We're going to hit Tab, and we're going to hit 50 millimeters and hit Enter. All right, so remember, one thing to keep in mind is wherever the cursor was, that is where that point is going to be. And notice that we can move this in and out. And this can cause a potential problem because then you lose the size of your circle. We don't have construction geometry. We don't have sketches in the traditional CAD sense. So we have to be very mindful of when we move these things around. You can go ahead and add a measured distance to this if you want and kind of get an idea of what this is. But notice that this is actually trying to be a horizontal distance from that point to the opposing point over here. If we come in between here and we right click, that's going to give us a point-to-point distance, and basically it's the diameter in this case. Now, if we want to change this, probably the easiest way to do this is to click on it, to go to your find search commands here. It's F on the keyboard, and start to type in dimension. And when you click on that, without the measurement is just there for our references, but you can just come in and you can type 50, and then you can have this on screen to make sure you don't accidentally move it and change it. Now, if you do happen to move this around, again, not a big deal. You can click on this, go to search, type in dimension, and you can redo that. So that's the only one there. But again, you do have to be on the circle. So I'm going to do Control Z, get back to where we're at 50. So once again, the location of that point is, if you need to snap to it, can be important when you're creating these circles. All right, let's go ahead and create the other circles. So center diameter circle. This one I'm going to snap here, and then I'm going to repeat that process. I'm going to snap this one here. And the big difference here, or the reason for this, is now those endpoints, the start end point of the circle, is on the x-axis. And then I can go to search and type in dimension, and I can reset that inside one based on our settings. So 47.5, and we'll do the same thing to the outside one. You can also repeat last command. Again, shortcut keys very handy. Shift and R will repeat the last command, and this one will be 52. But if you don't, you can go to search commands, type in dimension, and bring it up there. All right, so now we've got our inside one, and if we bring back our little spreadsheet here, we've got 47.5 for the inside diameter, 52 for the outside, and then the 50, the one that we have this measurement on, that's the point at which the teeth are going to intersect between two gears. And so this is now the basis of everything that we need to do in terms of the diameters. This one, again, is just a reference. We're going to be using it for a couple of different things, but for right now, it's just a reference. It's not going to actually create any geometry. So I'm going to pull this over to another window. I strongly suggest that you keep these numbers handy. We're going to be taking a look at the basically the tooth width at pitch and the circular pitch distance. We're going to take a look at those two numbers in just a second. So I'm going to pull this over to another screen. That way I can see it and you can't. And then we're going to start to create the first tooth. Now, most of the time, these teeth are created with arcs, but we're not quite ready for that arc yet. And the reason I say that is because first we need to define the pressure angle. That was that 20 degrees that we're using, and the width at these points. All right, and so what we're going to do is we're going to start a line, and I'm going to create a vertical line over here. I'm going to hit tab to go to that dimension, and I'm going to make this 1.58. Now, it was 1.5708 in our sketch. That 0.01 is not going to make much of a difference when we're 3D printing. Typically, for a tight fit, we're at 0.2 millimeters. For a loose fit, we're at 0.4. And so, again, 0.01, that's not going to make or break the distance. And so now this is effectively the width of our line. The problem is it's not in the right location, right? So it needs to be over here. And so what I'm going to do is I'm going to go to my dimension. I'm going to start to type in dimension here. And I'm going to make this half. I'm going to divide it by 2 and make it shorter. Now, the reason for this is because now I can move this line and I can build everything on one side and then I can mirror it to the other side. So we're going to use the move command. We want to use the freestyle option. You'll have to press F on the keyboard. There's nothing to click to make that happen. So F on the keyboard, and we want to move from this point, and we want to come down. And essentially what we want to do is we want to snap to this curve. Now you can see it's not really snapping where we want. That's okay. But for right now, we just want to get it close. Again, for 3D printing, we're kind of splitting hairs here. It's not really going to matter that much as long as we're getting these close, because we do need an applicable gap between parts to be able to 3D print them. Okay, so now we've got this. The next thing that I'm going to do is I'm going to start a line here. I'm going to start to drag this out. I don't really care about the length for right now, but I'm going to hit tab and tab again until I get to the angle, and I'm going to enter 20 degrees. Then I'm going to go to my find tools and start to type in extend, and I'm going to extend this line out until it crosses this inside diameter and the outside diameter. It already crossed the outside, but we're going to trim that back. And so this pressure angle, this 20 degrees, is our pressure angle that is going to dictate essentially the arc that we're going to create for this tooth. And so what I want to do from this point is go to my circle, hold down the left mouse button, and go to a center point arc. And I'm going to go from, somewhere over here below this intersection point, and somewhere over here below this intersection point. It's going to be really hard to see, and then I'm going to snap to that point right there. And it does not look like it created it. Let's go ahead and let's do a 3-point arc instead. Maybe that'll be better. So again, somewhere below on the circle, somewhere below on this circle, and then we want to snap to that point. And so essentially what we have now is, I'm going to hide this because I don't really need to see it. But essentially what we have now is an arc that is tangent to that 20-degree pressure angle at the point we're expecting the gears to intersect. At their full contact point, that's where we're expecting them to hit, and that's where we get that 20-degree pressure angle from. Again, that value is really used to drive all sorts of other things. You'll notice that we don't have a closed profile here. It's kind of showing us that we're missing something here. Don't worry about that just yet. This line isn't really needed anymore either. I'm going to go ahead and hide that. And then what I want to do is make sure that this, I'm going to hold down Control. I want to make sure that this snaps to those endpoints. If it doesn't, we'll come back and we'll fix it. But I moved it just slightly, and I tried to make sure that it intersected. If you zoom in, you can see that it's a little shy of it, but we'll sort that out in just a minute. I want to select this, and I want to mirror it to the other side. You can use this 3-dot menu here. This will have a lot of default commands based on your selection. We're going to select mirror, and then you'll have to come over here so you can kind of see this. We're going to click on this Y, and then right click, and now it's made it on the other side. And now you can see that we've got essentially our tooth profile. Because we don't need this outside diameter, I'm actually going to trim that. So you can come into some of these menus, and you'll notice that not all of these tools are active. Only Curve Array and Cut are active. Really, the tool that we want is Trim. And Trim can be found by default on this Curves menu on the left-hand side. It's also a shortcut T. So not everything is going to be in this menu. Most of our creation tools for curves are going to be over here, including Trim. We'll click on Trim and basically select that outside, and then we'll right-click to accept it. Don't worry about this one. Again, that's the pressure. That's the point at which the teeth are going to contact where we drove that 20-degree pressure angle. That's going to be a reference. We're going to hide it. It's not going to participate in the creation of that tooth. The last thing that I want to do is make a center diameter circle. So again, hold down the left mouse button. And I'm going to make this, so I'll hit tab. I'm going to make it 25 millimeters. And this is essentially the hub. In my example, I'm making them circular. Of course, if you need to drive this, if you need to connect it to a motor or a servo or something like that, you'll need a square drive or some sort of bolt pattern. For our purposes, we are just going to basically drive it like this. Now, a couple of considerations before we start building this into a solid. First thing we should think about is, do we want to extrude the tooth at this point and then pattern the surfaces, or do we want to pattern it as a body and combine it later? Now, I would argue that really what we want to do is extrude it here and pattern it as basically selecting those faces, because this allows us to easily add the fillet. Now, you might be thinking, well, maybe we want to do it as an instance, but if we want to modify the geometry at all, the instance really isn't going to be the best answer here, because we want this geometry to be basically something that we're creating and not a graphical copy of it. So I'm going to make this 5 millimeters thick and hit enter and hit enter again. And then I can hide all of my curves. So I'll just select them all in here. You can also hit H to hide these when they're selected. And then I'm going to rotate this around, select this edge, and we're going to add a root fillet. You have to be careful not to make this too big. You can also add one to the end if you want, but it needs to be big enough that you can print it, and it does add some strength, but you don't want to make it so big that the end of the other or the opposing gear is going to contact it. So I'm going to make it 0.25, and that should be okay. I don't know without seeing all the rest of the teeth, but that should be fine. All right, now we need to pattern this around. So I'm going to select all of these faces. I'll work my way around. Sometimes it's easier to turn X-ray mode off, so you can find that up here. That way we're not selecting through. I'm going to grab all those faces, and then I'm going to grab radial array. So from here, I need to select a center point and then the number of teeth. Now we decided the numbers were going to be 50, and so I'm going to hit enter, and now we've got our gear. That's basically it. We're done. So remember that the geometry was built with a 50 millimeter pressure angle. And so what I'm going to do is select the curve, select the solid, and duplicate these. So you can use Shift D, or you can select duplicate object down here. Notice the coordinate system is kind of pointing at a weird angle. What we want to do is reset the pivot. So you'll have to hit V on the keyboard, or you can change the pivot down here and the orientation of the pivot. And depending on where your object is in space, this might solve the problem for you. If you need to reset the pivot point based on your selection, then you want to use V on the keyboard. And so what I'm going to do is pull this over, and I want to pull it over to exactly 50 millimeters, because again, 50 is where those things are going to interact. And then the next thing I need to do is take that second solid body and I need to rotate it. So by default, it should rotate about the Z-axis at its origin. So you can come down here and to Z, and you can basically you can put in some values, or you can manually rotate it. And so basically we want to go about the Z-axis. And I don't know the exact angle. We could do some math and figure it out, but it looks like about 3.6 degrees should be fine. And then if we zoom in, what we should see is where these two circles intersect. Well, it doesn't work because they intersect right there, but this is basically the point at which the two gears are going to interact. And because we built an arc there, as they rotate, the contact point is going to move with it. And the way that we worked this out, we didn't include any backlash. We didn't do any calculations with the pressure angle. And I didn't include a lot of the math that goes into building this. But the way that we built this out automatically has a little bit of a gap in it. So you don't necessarily need to offset these too much for 3D printing. If you have a printer that isn't super accurate, then you may want to include a little bit of offset, which you would do probably before you built the tooth. You may want to reduce the size a little bit. And you can include all of that in your own spreadsheet. And basically you want to reduce the tooth width. But now everything that we did to define these is good to go. Now I 3D printed this exact set. Well, not this one here, but the one that I drew before this, and I used the same numbers for the module and the number of teeth and everything. And then basically I added a little bit of slop in the distance between the 25 millimeters and the piece that this went on. So I did 24.8. So I had that 0.2 millimeter gap, and that allows, enough slop between the two gears that they're not binding up or moving at all. If you try to do this with zero gap or zero tolerance in here, they likely will be too tight to print. But again, you'll have to play around with your own printer to see how it works. Now that we have these, you could build a base plate. I'm not going to walk through that process because that's just a couple of extrudes. And then you can either select the bodies and go into search and do export STL. So you can go directly from here and export the STL. The density going this way, you'll notice how this is getting converted. You can also use some various options here. I will generally say that what I do is I take the entire file and I go to export and I do an STL this way. And I'll just go ahead and show you the process here. And again, it brings up the same menu, depending on your selection, if you don't have anything selected, it'll take all the solid bodies that are visible. If you do have a body selected, it'll go to the same thing that you're doing there. So the menus get you to the same place, whether or not you select it on screen and you do export here as a 3MF, OBJ, STL, step file, works in most print slicers. You can bring those in as you see fit. We're not going to go through the process of printing this again, but I do think it's important that we just take a quick look at slicing this. I'm going to use Bamboo Slicer. I've done videos on the Creality Slicer and Bamboo Slicer. You can obviously use whatever slicer that you have. When you bring them in, they will be a single object, and so you'll need to break them up. If you're exporting them all together as one, you'll need to break them up. I'm going to go ahead and pull these apart. And then when you slice the plate, the one thing that I would say is be careful with the number of external edges. We'll kind of bring this down, and the infill that you use. And so I typically will want a couple of layers inside of where the tooth is for strength. I typically will not use the gyroid. And so if I go back to preview and just select this gear here, for strength, just for speed's sake, I typically would use something like a grid. And then you can also come in and increase the wall loops. Now this is global settings here. You can go and you can drive way down the rabbit hole. But basically what I do is I use global settings, make sure that I've got enough traces inside of the teeth, so I've got some additional strength there. That way they're not going to be breaking at that point. The inside really doesn't matter too much in terms of transferring the load because the top and the bottom layers are going to take most of that. And then again, the number of traces around the hub. If you're driving this with a square pattern or a bolt pattern or something, you'll want to have a little bit of extra strength there. So that's the way in which I would slice this. And again, just kind of very general sense, general numbers. But you obviously should have experience in whatever your slicer is that you're using and whatever settings you like. Just make sure that you do ensure that, especially as you make larger teeth, that you do have those extra traces around. So that way the teeth, it's really the part where you need the strength. The hub, again, the top and the bottom layers are going to carry most of it. The infill internal stuff is not going to have too much of an impact on the strength of these 3D printed gears, at least for most applications. Hopefully that helps. I know that ended up being a fairly long video, but unfortunately math is math, and it is important when we're trying to make things like gears. So make sure that you do spend a little bit of time and just understand what these values mean. Again, pitch diameter is going to be the diameter where the two gears basically have their contact point. That's driven by the number of teeth and the module. So you increase the module, it's going to increase the pitch diameter based on the number of teeth. So if you're trying to get to an end result of a diameter and a number of teeth, then you want to make sure you understand what that module value is doing. If you want 50 millimeters and only 25 teeth, then you use a module of 2. Typically, that module value is going to be fairly large in many cases, which will give you a large tooth, which means that if you're trying to basically transition between different gears, then you need to keep that in mind. You can make larger gears and smaller gears. You want to make sure that you keep the module the same between them. The number of teeth is not going to have as much of an impact in how the gears mesh together, but that module will directly affect it. So for example, if I increase this to 50, notice that the pitch distance, the distance between two teeth, and the width, those stay the same. Even though I've increased or decreased this number, the pitch diameter is what's changing here. So if you're trying to get a 2-to-1 ratio, for example, make sure the module stays the same, and then you change the number of teeth, and then look at the rest of those parameters. As far as the rest of these numbers, these are basically just trying to get us to the OD and the ID values. So the addendum and dedendum, you could calculate these directly inside of these two parameters and not worry about those at all. These numbers are just kind of, again, the circular pitch distance, that's just kind of a reference there. You don't really need it because the tooth width is going to kind of drive drive that value anyways. So that's just another sort of sanity check reference number that I use when I'm creating this stuff. And last disclaimer, just before we sign off on this, make sure that you understand that these are not mechanically sound machined parameters for a spur gear. These are basically a mathematically reduced version of a spur gear for 3D printing, because the strength and all the different settings that you really need when you're trying to design a mechanically sound machined, set of gears is well above what we need for 3D printing. So it's just beyond what we needed to configure for this. I will go ahead and I'll put this information in the description of the video, and I'll also leave some other links and stuff in the description of the video. But if you have any questions, please let me know. As always, thanks for watching, and we'll see you in the next one.